Hi everyone. Today we'll be presenting a paper, Multi-Camera, Multi-Person Tracking with DeepSORT and MySQL. The authors of the paper are Shashank, Yashasvi, Nehashri, and Hrithik, who are students of RV College of Engineering, Dr. Ramakanth, Dr. Azra, and Dr. Sreelakshmi, who are from the Department of Computer Science and Engineering, RV College, and Dr. Neeta and Ashish, who are from Inference Quotient Private Limited. So, in recent years, we've witnessed significant advancements in computer vision, especially related to object detection and tracking, which are both critical for applications like surveillance and autonomous vehicles. Object detection mainly focuses on identifying the position of an object in an image, whereas object tracking involves predicting an object's movement across video frames using both the spatial and temporal attributes. The YOLO V4 algorithm plays a key role in the detection stage, effectively identifying objects in real time. For tracking, we utilize DeepSORT, which is an extension of the SORT algorithm. DeepSORT incorporates various deep learning techniques, such as a Kalman filter used for motion prediction, as well as frame by frame data association, which is done by the Hungarian method. Additionally, it also employs an appearance descriptor, which is generated by a convolutional neural network. By using all of these approaches, it ensures efficient tracking and provides a robust solution for multiple object tracking tasks. Despite all of these advancements, object tracking in a multi-camera environment presents various challenges. And one of the major issues is occlusion, where objects may be partially or completely hidden from view, which complicates the tracking process. Current tracking systems often struggle with maintaining these object identities in the presence of occlusions or when objects move from overlapping camera views. This challenge gets further compounded in multi-camera setups where synchronization as well as data integration are crucial for accurate tracking. Various techniques have been proposed in recent research to enhance this tracking accuracy. However, many of these techniques are still unable to handle these complicated scenarios. This study proposes a novel strategy to address extended occlusion, reduce identity switches, and introduces a database system for seamless track information transfer between multiple cameras. Now Neha will take over.
The second section of the paper discusses about the enhancements that we have done to the original DeepSORT. The DeepSORT code was modified in order to reduce any identity mismatches and cases of occlusion. This was done with the help of addition of new track states and also by stopping the visual feature updates. Occlusion handling. In the context of occlusion handling in a single camera scenario, it is important to address situations where one person is standing exactly behind the other person. That is when multiple people are actually present in the same bounding box. So occlusion handling is what is trying to prevent the visual feature updates that can lead to confusion and identity exchanges among the individuals. Partial and complete overlap detection. The intersection over union metric is used to determine when partial or complete overlap takes place between two tracks. The amount of overlap between any two bounding boxes is measured by the IOU. If IOU value between the two matched tracks is greater than the IOU threshold, then it is considered as a partial overlap. And if the IOU value between a matched and an unmatched track is greater than the IOU threshold, then it is considered as an complete overlap. Stopping the appearance feature updates. In case of the above two cases, that is partial and complete overlap, being true, the update function is modified in order to update only the movement features of the track instead of updating both the movement features and the appearance features. Avoiding identity mismatches is another enhancement where the tracker reduces the possibility of inaccurate identity mismatches by stopping the appearance feature updates during occlusion. This is because when a number of people are present in the same bounding box, the distinguishing feature, that is the feature appearance feature vector, will become inaccurate and unclear. So the tracker can preserve each person's track by reducing the likelihood of identity exchanges, since we are giving more priority to the Kalman movement attributes. The third section discusses about the experimental setup for the research. We first recorded multiple videos for the single camera scenarios and multi-camera scenarios. Now the videos were recorded at a significant height in order to allow the camera feed to be able to capture a wide area. The videos were then downloaded and processed via our code in order to determine the accuracy and consistency of the code. Table 1 represents the instrument or device that was used for capturing the videos for single camera instance, and Table 2 represents the camera that was used for capturing videos for multi-camera instances. Now, two of these cameras were installed at a height of 4 stories. Now, the two cameras were, let's say, named as Cam 1 and Cam 2, were set up at a point of height towards the field. Now, both the fields were capturing at a resolution of 1920 by 1080. Cam 1 captured the left area, whereas Cam 2 captured the right area. And between both of these capturing fields, there was an overlapping region. A large part of the feed beside this overlapping region was considered as the writing region. So whenever a track entered the writing region, its features were written into the database, which was immediately read and stored by the other camera. The coordinates for the overlapping line and the writing region is mentioned in the paper. The next section will be explained by Yashasvi.
Yeah. To run tests on our extended algorithm, we had to select certain amount of data. So the criteria for data selection is as follows. So any acceptable data feeds would be one that focused on occlusion, which was the main focus of our paper, and anything where the detections were moving at varying speeds. And also if the video had any number of people and as long as they were detectable. For out of scope criteria, it is one, the detected object is not a person. YOLO V4, which is the detector we use, can detect other objects, but our paper focuses mostly on people. So if it was not a person, it was out of scope for us. And also, like I said, they need to be detectable. Now, coming into the footage, we have footage for the single camera and multi-camera. For single camera, we focused for 7 scenes of 7 different cases, and multi-camera, we have 10 different cases, which will be covered in the later section. So points to note about the single camera footage is we have 7 cases and they mostly fall in 2 types of categories. One is where the IDs are exchanged and new IDs are assigned within that video due to, let's say, crossover or occlusion. And the second type of scenarios that we faced was when IDs disappeared and then were later reassigned. So yes, each of the cases had small changes like what was occluding them and things like that, but they fell into overall these 2 types of categories. So moving on, why do we need these modifications is, well, one, the original DeepSORT code focuses mainly on the single camera tracking, and also it does not handle occlusion situations very well. Now, to get over this or to improve the code from this, we have included a few changes. One of them being we have introduced 4 new states. And the existing states were confirmed, deleted, and tentative. But the 4 new states that we introduced were the inactive state, occluding, person occluded, and object occluded state. So the occluding state and the occluded states are pretty self-explanatory. If a track is hiding another track, would get an occluding state, and the occluded state is if that track was behind another track. So person is if a track is occluding the behind track, and the object occluded is if that track was covered because of some tree or some static object that is not being detected. Now, coming to the inactive state, that is for when a track disappears for a period of time and you want to reassign it later. In the original DeepSORT, what it would have done is it would have checked for a maximum of 60 frames, and if it wasn't detected before that, it would automatically delete it. Here, instead of doing that, we're adding it into a new state called inactive, and it is still eligible for track matching. Now, moving on, after this, we've also included some few more features like the awk pairs. So like I said, awk pairs is a list of pairs, and each pair includes one ID from the occluding track and an ID from the occluded track, and usually it's the occluding and person occluded track. This is basically to make sure that the occluded track, so that is the track that is covered, does not get a confirmed state unless the occluding track, which is the track in front of it, gets the confirmed state first. And apart from this, there is also a 2-alphabet generator, which we've introduced. So that is kind of like a two-step verification to make sure that no two tracks at any point of time will get the same track ID, or the possibility of having the same track ID is very low. So having a track 1AB and a track 1CD are two different tracks. And after that, we've also included a database. Now, this is essential for multi-camera tracking to share data between the two cameras. Now, we've chosen MySQL database. As you can see, the read and write performance metrics as compared to the MongoDB database were much better, and it also was more suitable for the existing system. Then coming to the schema of the database, we have two tables. We have a feature table and a shared table. Now, the feature table is a table unique to each of the cameras in the system, and the shared table has data that can be changed by any of the cameras. Now, the feature table stores the track ID, the track state, any features like the appearance vector, frame number, the number of hits, the mean and covariance vectors, the two alphabets that we have, the age, which is basically the total number of frames that have passed on once that track has been detected, and also if that track is occluding another track, that ID. Now, the shared table has a normal index and the next track ID, which should be assigned. And it also has communication flags, which is basically used to identify that, okay, a camera has data which is unread from its feature table. Now, moving on, Shashank will continue.
So I'll be explaining the implementation section now. So first of all, we have a single camera tracking implementation. So here the process begins by loading the necessary libraries, including the YOLO object detector and also the DeepSORT metrics. DeepSORT assigns these detections to existing tracks using the IOU metric and also feature similarity. Then the tracks are updated with Kalman filters and special state like we've included, like occluding and person occluded. They can handle the overlaps and prevent identity mismatches. Tracks become inactive if they aren't updated within the defined frame limit, which is given 60 frames, and they can be active again if they come back into the screen. So this is the gist of the single camera tracking implementation. Now moving on to multi-camera tracking, we can see that you have to keep in mind that whatever we did for single camera applies here as well. And along with this, there's some additional things like the database, which is MySQL implemented here. So here we assign unique DeepSORT trackers to each camera and then use a shared database to ensure proper tracking across the two feeds. Tracks are defined within these regions and are logged into the database. And we have regions such as the overlap region and the writing region. So whenever a track enters the writing region, the tracks are written into the database, and then the reading from the database happens from the other camera. So basically, the other camera knows that there's a person with these features in which is not even in its feed, which is a very novel approach. And this coordination also ensures smooth cross-camera transitions, and it doesn't lose object identity. So in both these scenarios, the system outputs are quite similar, but in the multi-camera, you have the regions also defined using some colored lines. Now, DeepSORT reliability in handling occlusions and multiple feeds makes it an essential tool for us. Moving on, we have the results and discussion section. So the first three paragraphs of this section describe what we've mainly worked on and also what improvements we've made to existing studies and also what limitations are there which can be further explored in future studies. So the innovations, as I explained before, are stopping of visual feature updates to ensure proper identity matches, and also MySQL has been added. So moving on, we have, first of all, we have single camera results. So this graph explains the single camera results very well. It's a line graph which shows the performance of original DeepSORT to our enhanced version of the DeepSORT on the same 7 videos. The x-axis represents the number of the video and the y-axis represents the accuracy percentage. So here the accuracy percentage is basically calculated by the proportion of frames with correct ID assignments relative to the total number of frames. So here, as we can see from the blue line, the accuracy is very less for original DeepSORT. This is because after occlusion, they're assigned new IDs which weren't their original IDs. So all of those are wrong assignments. And from the red line, we can see most of them are above 90% and close to 100 even, which shows how efficient our enhanced DeepSORT is with occlusion handling. Moving on, we have some figures which show the outputs in single camera videos. So A and B represent the original DeepSORT. As you can see, the identities have been exchanged and a new ID has been assigned, which is not really ideal. C and D show the new DeepSORT, that is our version. As we can see, the track IDs after occlusion are similar or the same as to what was before occlusion. Along with the ID number, we also have alphabet codes and the track states also mentioned. Another novel thing that we did was derive the state matrix from whatever we have observed in these videos. So there are what the state matrix basically describes is what condition it takes for a track to go from one state to another state. As an example, from inactive to confirmed state, if it has to go from frame to frame, it has to be back to screen after going out for greater than max stage frames. So every cell in this matrix represents the change conditions, and the hyphens represent either that is the same state or that it can't go from one state to another state. Moving on, we have multi-camera results. So in this section, we describe the outputs on multi-camera videos that are the 10 videos that we filmed. First of all, we have these two images to show how the output looks like. So if we see one of the images, you can see the cam number, the frame number, the next IDs such as COM1 and COM2, and also the track number, alphabet code, and also the state. And on the bottom, it also mentions which camera is writing into the database as well. And the two lines represent the regions that we've mentioned before. Finally, these describe the results of the multi-camera footages on enhanced DeepSORT. There are 10 videos, the description of all the 10 videos, and the outputs on all the 10 videos, which shows what output was observed. Now we have the caveats and limitations. These 4 limitations were some minor roadblocks that we hit, which can be explored in the further studies, such as incorrect assignment of some states and also the regions that we have defined. Sometimes there is no writing, and it can be different IDs can be assigned across the cameras if it newly appears there. These are very edge cases, but it provides a platform for further research. Now Hrithik will conclude the presentation.
Yeah, in conclusion, this study presents significant enhancements to the DeepSORT algorithm by successfully maintaining the IDs of multiple individuals on camera even after occlusions, which was not feasible in prior implementations, and by creating a detailed track state at every frame and introducing these new states. The research lays the groundwork for more accurate and comprehensive tracking algorithms. This work represents a meaningful step forward in the field of multi-object tracking, offering practical solutions and opening the door to new research opportunities. Thank you.